Good morning, everyone, and welcome to this webinar on CFD applied in the biomedical sector. My name is Alessandro Palmas, and I am one of the founders and developers of Consolve. And today I'm going to present to you how to apply computational fluid dynamics to simulate the hemodynamics, so the blood flow inside a coronary artery. First of all, a few words about Consolve. This is our mission. We want to help innovative small, medium enterprises and freelancers improve engineering design of their products. And we want to do that providing design software easy to use and accessible everywhere. So our core business is the CFD on cloud. In fact, with Consolve, we provide a CFD software you can use directly into your browser. Besides these main products, we also offer consulting with dedicated development activities as well as product optimization, and then support with qualified technical personnel as well as events like these webinars and training, both on-site and remote served. So now let's focus a little bit on the CFD on cloud product, just to highlight some features and how the simulation is organized. Then we will perform a live simulation about the blood flow, and you will see the Consolve at work. First of all, the advantages of the CFD on cloud. If you want to perform a CFD analysis, you have to withstand very high investment and costs. In fact, license, hardware, and know-how can raise up to 100,000 euro per year. So with our solution, you can forget about license, for example, since you can rely on the software as a service approach, and you may pay just for the simulation you need. Using our cloud, in order to compute your simulation, you can avoid processing hardware with high performance, and so you can run, for example, the CFD simulation even from your tablet. About know-how, we provide vertical application as well as automated workflow, and you don't need to be an expert anymore. Finally, the budgeting is not more needed since you can charge directly on the customer the simulation, since you are going to pay just for the simulation time you will be using. This means savings up to 90% if compared with most standalone software diffused nowadays. If someone may argue that experiment can be a different way to perform the same task, well, there is a huge difference between experiment and simulation in a variety of fields. For example, the number of parameters you can analyze with experiments are limited, while simulation allows for a wide set of analysis at the same time. The same thing can be said for spatial and time resolution, as well as the test scale available. You can imagine what would mean to put an entire airplane inside a wind tunnel. It's simply not possible, while with the simulation you can perform real scale simulation. Another advantage of the simulation with respect to experiment is that the virtual environment allows you to perform dangerous studies that cannot be achieved in an experimental way, such as explosions, for example, or contaminant simulation. So now, let's see how the simulation workflow is organized inside Consolve. There are 4 steps. The first one is the geometry one. You have to create your model, your CAD model and then upload it on our web platform. You can then define your geometrical grid that is called also computational mesh. And basically, it means to subdivide your domain, the region you want to simulate, in small elements called cells. Then you have to define your CFD setup. It means choosing model and boundary condition of your problem. Finally, when the CFD has been completed, you can analyze results. So let's now see in details every step and highlight some major features. About the geometry one, you can upload your model in STEP, IGES, and STL format with both international system and imperial units of measure. We can also allow you to create automatically a wind tunnel for external flow, such as external vehicles aerodynamics. Now, about the meshing, you have to choose between hexahedral and tetrahedral meshing algorithms, with also a boundary layer for word refinement that can be available. And another important thing is that our procedure is guided, and so you first can perform the surface mesh, and then the volume one, it allows you to deal with meshing in a very straightforward way, as we will see very soon. Now, about the CFD, you can choose between incompressible and compressible flows, laminar and viscid, and turbulent ones with major turbulence models available. You can see here K epsilon, K omega, and Sparta Talmaras. Finally, both steady and transient simulation can be performed with console. One thing we want to stress is that since we rely on OpenFOAM open source library, our code can provide you accurate and validated results, since this library is maintained by a large number of university and research centers across the globe, and it is always being validated and tested to assure you meaningful results. Finally, the last step is the result one, may be the most interesting for the user, where he can gather that data from its simulation, and we provide you the web-based version of ParaView, a well-known post-processing software to analyze scientific data. And ParaView has a number of features available in terms of filters to be applied on your simulation result. You can, for example, extract slices, as well as streamlines, draw contours, and extract profiles. We will see some features today in our webinar, and more will be available in the near future. Apart from what I just described, we also offer some features that may be hidden in the offer, but we want to highlight them here in this slide. We offer support directly online, and we can provide you help directly on your case, since the web platform can be used to share your work environment with remote location. We offer you test cases and tutorials. You can find them on wiki.consult.com. They can guide you through the correct setup of a wide number and variety of cases, as you can find. And as you can see, as you will see today, we are going to use the manual, the wiki manual, in order to complete our webinar. Then hardware resources. Our cloud is available 24/7, and you have unlimited power of computations, since you can rely on the cloud. Finally, software development. We can provide on-demand software development if you have any specific need, any particular requirement for your simulation. We can also provide you a vertical application tailored on your specifications. So now let's focus on the main part of the webinar. So the CFD analysis of a blood vessel. First of all, let's take a look at the geometry. This on the left, colored in blue, is a left coronary artery, a complete scannerization of it, and it's a courtesy of Politecnico di Torino and the equipe of Prof. Morbiducci that provided us with the geometry. And we will analyze a subset of it, the highlighted one with the orange circle, and that is represented on the right side on green. It's the terminal part of the vessel, and we will analyze the velocity contour inside the vessel as well as the flow lines. And you will see how everything can be very explicative in terms of how the flow behaves interacting with the walls of the vessel. So the file we are gonna use is a step file that is the best one because of its flexibility. First thing to do with your CAD, you have to colorate it. In fact, the AP214 allows you to assign colors to your surfaces. And it is very useful to define boundary condition as well as surfaces. And here, for example, we highlighted the inlet that we colored in yellow. Then we have 4 outlets colored in red and other colors. And finally, the walls that are left green. That is the default one. So now that we have our geometry prepared, we can shift to the website, our web application, and show you how the simulation is performed. Well, as you can see, I'm in a common browser. In particular, I'm using Google Chrome. And we are on our home page, concept.com. We can, in order to log in, we can just click on the top right of the page on the button Login, Sign Up. If you have an account, you can log in here. Otherwise, you can directly register here in 2 clicks. I'm going to use the Conself account. So just let me introduce the credentials. And that's it. I am inside the web application. As you can see, there are 2 tabs, the dashboard one and the simulation. Well, the dashboard provides you some information about your account, in particular the remaining credits and the used ones, and also some other information that will be more clear later. Now we can just skip to the simulation tab. As you can see, there are also user manual, link, and contact support right in the application. So let's now start with a fresh new one case. Let's call it BioMedical, and let's click Create. This directs us into the workflow of the simulation. As you can see here, there are the 4 steps. They are 5 because MASH is split in 2 parts. And we have to start from geometry. So now we can upload our file that is, in my case, is lca.step. And this way, the system uploads the file inside the application. You have to wait until the upload is done. It may take a while. It depends, strongly depends on the dimension of your file. Anyhow, there are no limits. It depends also on the speed, on the upload speed of your connection. So we are halfway. Just wait a few seconds more, and I will show you how you have to deal with the first step, with this particular one. So, as I told you, the LCA file is a step file with colored surfaces. The colors identifies boundaries, and we will use this definition in the CFD step. Okay, now we are almost done. That's it. Now we have to choose the units and the grouping criteria. Since we define the colors, we have to choose the grouping criteria by curve color. This way, we will have the geometry divided depending on how the surfaces are covered. Then we click Next, and we are in the domain. We have to choose if the flow is internal or external. In case of external flow, you have to define a bounding box that will be your wind tunnel, and it is used, for example, in case of external aerodynamic studies for vehicles. In our case, it's an internal one. You have to click Submit. This way, I'm not doing it because I already have a webinar case ready for us, and I'm not launching another one right now. But when you click Submit, it's something you have to do at the end of each step. You will see your step running right here under Case in Progress with the progress bar, at the end of which the case will be shown inside this select here. So let's now skip to the webinar BioMedical I already prepared and open it. Okay, so the geometry just run, and we are in the Mesh 2D step. First thing to do is to choose the step from where to start our simulation. So we just run geometry, we select it, and as you will see, the geometry, it will be loaded in our graphic window here on the right. It's our geometry, and with all, if you want, I can show you that the geometry is splitted in colors. If you select File and then go down, and here there are all the different boundaries. Let's say I want to, the yellow tree is the inlet, so let's click Apply. Let's show the graphic, and here it is. This is the inlet. So for each of them, you have to assign the refinement mesh for the surface. Now, it's for everyone, it's okay to use 0.01 with uniformity level 70, and you have to do it for every boundary. Then you can click Submit, and you are good to go, and your step mesh 2D is completed. So let's skip the Submit and just go to the Mesh 3D case step, where again we have to choose from where to study. We just completed Mesh 2D, so we choose that one. As you will see, again the geometry appears here. Now, what's the main difference with respect to the previous step? Well, since we just run Mesh 2D, we have a surface mesh that will be very, very refined according to our choice. So now let's see how it is shown, and you have to select surface with edges from the menu on the representation. Click Apply, and then here you can see, if you zoom in, this is This is the surface mesh resolution. Now, since we are good with this mesh, otherwise we can just go back to mesh 2D and resubmit another step with a different mesh size specification. But it's good for us, so we can select the algorithm. Let's select tetrahedral with boundary layer, and the max element size is okay. Let's click next, and we are redirected to the boundary treatment. How can be selected the boundary treatment for each boundary? Well, if you have any doubt, you can use the user manual. It redirects you towards the manual page, and under Mesh 3D, you can see a description of the volume mesh algorithm. Here you can see the difference between ixohedral and tetrahedral one, and also how the boundary layer performs. It basically allows you to specify as a particular near wall mesh with the wall cell A and the layer number. In our case, we don't need anything in terms of wall prescriptions, so we can just submit after selecting one of the boundary. This will perform our volume mesh, and again, we skip this part going through the CFD right away. Here again, just select the 3D mesh from where to start from, and that's our mesh 3D. We can also take a look at the inside of our blood vessel, since now we have a volume mesh inside. Now let's select our file, then click on the plus and choose slice. With the slice selected with representation surface with edges, just click OK. And as you can see, we just cut our domain, and here they are, the cells inside our vessel. So we are good to go. We can proceed towards the CFD setup. First thing to do is choose the density model. We want to perform an incompressible flow simulation with the turbulence model with spiral mass. Density, we apply 1060 for the blood density. A pressure, since it is an incompressible flow, we can use a reference value. We will use 1 for the initialization of the pressure and 0 for velocity. About viscosity, we apply 0.0035 kilograms per meter second. Finally, spiral mass viscosity. This is the default value, and usually it's okay since it's just a turbulence initialization. Now, let's proceed towards the boundary condition assignment. Starting with the walls, that's yellow. Well, the default values are okay for the walls, since we have a 0 gradient for both pressure and spiral mass variable, as well as 0 value for velocity. Let's now focus on outlets that are all but the last one. Outlets, we can assign a value, a prescribed value on pressure that can be chosen as 1, and then 0 gradient on the other variables, spiral mass as well as velocity. Okay, so our outlet is okay. Now we have to do the same thing for all the 4 outlets. Finally, the inlets. Starting from the simple one, we have a 0 gradient on pressure. We have a prescribed value on the spiral mass variable, which value you can find some hints about choosing the value. In our manual, again, on the boundary conditions section, there are some formulas that you can use depending on your flow. It gives you the value to insert here. We are just putting the initialization value. It's okay for our purpose. And finally, the most tricky thing is the assignment of the velocity values. Well, we want to assign a uniform profile of 0.1 meters per second across the section. But we have a problem since the section of inlet, the surface, is not aligned to any axis, no X, no Y, nor Z. So we first need to identify the normal of that surface and then to project our velocity vectors on the three components. In our case, the values will be along Z minus 0.056, on Y 0.078, and on Z minus 0.0255. That's it. We are clear now to proceed to the last step of the CFD. So click next, and now we have to choose the time evolution. We want a steady simulation. You can also choose transit, but this one is a steady simulation, 1,500 iteration, and safe solution every, let's say, 100 iteration. So now we can click submit, and again, the CFD step will be shown on the dashboard, on the simulation tab under the window case in progress. But let's say we already performed that and go to the result, last and maybe most interesting step. So let's upload the CFD result, and you will see again our geometry shown here in your graphic window. So it's one important difference. There is one important difference between this geometry here and the other ones we just saw in previous steps, and it's that associated with this geometry you have your data. So velocity, pressure, and so on. First thing to do is to click on this small clock and to go to the last iteration. This way you will have your data loaded as they were evaluated on the last iteration step, so at the end of the simulation. Now, first thing we want to do is to cut our vessel and to see inside it how the velocity is behaving with respect to its interaction with walls. First thing, okay, we want to see the velocity. Then let's apply a slice filter on our system. And again, here we want to see the velocity. But also, let's move the slice, in order to highlight the part we are interested. So the X origin, the X origin value is 0.0732. The Y is 0.09959. That is 0.08102, while the normal is minus 0.1036, 0.8269, and 0.7721. Okay, well, now I can just click apply, and you will see our slice right here. Well, how did I manage to find these values? Well, it's just a trial and error. Here the point is our vessels developed in 3D, so it's impossible to have a plain slice that cuts everything to show the inside of the vessel. So you have to move the slice in order to adjust its position in terms of normal and origin point. Then here you can adjust the maximum value of your contour in order to highlight the zone the range of velocity you are interested about. Let's say it's from 0 to 0.15. And so here we are. Here, this is the inlet. This is one outlet. Here there is branch where there is another outlet, and so on. And you can see how the flow performs. Now, this this was one of the aspects we want to analyze here. The second one are the trajectories, and again we have to apply a filter. You can find here string tracer. You have to represent it choosing vectors. U, the color we want to represent. Okay, well, let's just first define the source point, and we can choose Z 0.0693, Y 0.0865, and Z finally 0.09166. Number of points, we will see how this influence our plot. Let's keep everything as it was. Click OK, and you will see here you have very few streamlines. In order to have a larger number of streamlines, just add here 0, 0 on the number of points, and now when you click apply, you will see a high number of streamlines defining your flow. Again, instead of coloring it by a solid color, you can choose the variable you want. Let's say U. Let's say click apply, and then here modify the range, and that's it. So here you can see we have the flow describe a trajectory of the particles and how it behaves inside the vessel. If you want, you can also add the geometry, and in order to see inside it, you can just apply here the opacity of a value less than 1, lower than 1, and that's it. You can see inside. So these were two filters applied in ParaView. You can have many more, as you can find in this list. There are a lot of things you can do with ParaView. If you need something particular, we are here to help, so don't worry. And many more will be added soon in order to allow you to perform a very wide set of analysis. Now let's get back for a second to our presentation. So okay, so we just completed the practical application, and a few words about extended features. Well, there are a lot of possible advanced features we can provide, and we will provide. Two of them are listed here. For example, variable viscosity models that are usually important in this kind of simulation, and also user-defined profile at inlet. In fact, we just performed a simulation with a uniform profile. It means the same value in every part of your inlet. It means here a plate that will enter your domain. Instead, usually, in order to be the accurate in your simulation, you have to assign a profile that is different, and it changes depending on your coordinates. So soon we will be able to provide you also this functionality here. Now, questions. If you want to ask us some questions, you can use the question and answer tool embedded in Hangouts on Air that we are using. You just go on the top right, click on that array of squares, and then click on question and answers. Maybe you, for sure, you will need to be logged in into Google+. So Anyway, if you cannot ask questions, you can write us to our mail address. You can find it here. You can log in our website and follow us on major social networks as well as YouTube. You can find there a lot of webinars, and in order to keep up to date yourself with our CFD webinars, just register and subscribe there. Now, I will propose you some questions and that usually users ask, and if you need anything else, just write on the screen. Now, usually they ask us, what happens if I'm running a simulation and my internet connection goes down? Well, it happens basically nothing, since our servers will complete the simulation and save the results. So in fact, once you just submit your simulation, you can also turn off your PC and come back later. Another question is, what's your subscription plans? Well, we offer 4 different plans. 2 of them are monthly billed and 2 of them are annually billed. They differ mainly in terms of credits you have, and so it means in numbers of simulation you can perform in that span of time. Another question is usually, do I need any particular hardware to run the simulation? Since it runs on a browser and on our cloud, you can use it also even from your tablet, for example. Anything that has a browser can be used to set up our simulation. Compatibility towards browsers and operating systems is very wide. We tested it against major browsers like Google Chrome, Mozilla Firefox, Internet Explorer, and Safari, as well on different operating systems, Windows, Unix-based systems like Linux, and OS X. Now, about a few words about privacy. If you're worried about the privacy, well, we offer the most recent standards in terms of privacy protection. And if you are very, very worried about, we can provide you also dedicated solution with privately owned servers, and that can be the best solution if you have some particular needs in terms of that. Another question that all users usually ask us is about the co-working space. If more than one user can use the same credential, and the answer is yes. With your credential, you can access it at the same time from multiple locations. And in fact, this is a wise choice in order to share a co-working space where to collaborate with your colleagues, even from remote locations, and to share the same simulation as well as procedures. Well, that's it. If you don't have any other question, I just thank you all for watching. And in case you have any inquiry, just write us or contact us through our website. You have here all our references. So thanks again, and now have a nice day.